Okay, so I'm going to move down in scale a little bit. I'm going to talk a bit about cells and cell imaging. And cells are obviously important, you know that more than I do. And one of the difficulties that we have, even with the advances in microscopy that we've had over the last 100 years, is seeing inside the cells. And that's largely because of the scales involved. Cells are 10 microns across, and all this interesting structure is smaller than optical microscopes can see. They don't have contrast at those scales anyway. Electron microscopes can't penetrate objects that thick, and fluorescence microscopy just allows you to see where the lights are, like the ones that are blinding me now. 20 years ago or so, scientists started to develop at synchrotrons, which are football stadium-sized billion-euro light sources, type of microscopy that they could do with X-rays that penetrate through about 10 to 15 microns of water, but that are absorbed preferentially by carbon and nitrogen. So using these X-rays, they were able to get natural contrast on biological material. And they can get high resolution because the wavelength that they're using to do the imaging is around 2.5 nanometers. And the sample preparation, because they don't have to do anything to stain the cells, the sample preparation is simple. They drop the cells into liquid ethane and they're frozen, and that's it. When they do that, they can image the cells and produce a quantitative map of what's happening in there. They can get a linear absorption coefficient map of the inside of the cell in the same way that you do with CT scans. So it's just a miniature CT on cells. So this has been applied at synchrotrons, and people can segment out things that are of interest to them. So for instance, in this study that was done at a synchrotron, they were interested in changing the genes of a particular yeast type and looking at the effect that it had on the mitochondrial distribution. I'm not a biologist, and it's all lost on me as to why that's particularly interesting, but they seem to find it so. Another thing that's maybe a little bit more obvious, they looked at the life cycle of the malarial parasite, and they were able to look at that inside in blood cells and look at, for example, the way the parasite sequesters the iron from the hemoglobin it digests into nanoparticles inside in the cell. And that just gives you an idea of the power of the technique, that you can follow nanoparticles in unstained natural cells. Another powerful aspect of the technique is that it's compatible with and complementary to fluorescence microscopy. So you can take the same cells and take fluorescence images of these cells and superimpose the fluorescence images, which give you chemical information, on the X-ray images, which give you structural information. And that's very, very powerful. So as I said anyway, this technique has been developed over the last 20 years at synchrotrons, and not everybody has €1 billion to spend or a football field size available to use it in. So in the School of Physics we've developed, and in the Atomic Molecular and Plasma Physics group where I work, we've developed a light source which is able to illuminate samples in a microscope like this in the same way, but the microscope is this size instead of football stadium size. So this technology of a light source that can illuminate cells and allow this imaging to be done is being developed in a spin-out company called Sirius XT. There's 15 scientists and engineers working up there at the moment. We have one scientist working in the Conway Institute at the moment now at the same time, working on developing complementary cell preparation techniques and fluorescence and cryofluorescence imaging. And the company will, as part of its development plan, put one of these microscopes into the Conway Institute over the next year. And the idea there is to have an imaging service where people who are interested in exploring the possibilities of this technique can do this locally here in UCD. And it will allow us to develop demonstration of the technology, obviously. So that's why it's important for the development. How does this fit into the Centre for Physics and Health and Medicine? So I suppose at an early stage, it's going to be in looking at drug interactions with cells, maybe looking at nanoparticle take-up and where the endpoints are for nanoparticles in cells, looking in disease pathways and radiation damage, for example, at a cellular level, to see what way things are disrupted and what parts of the cells are most affected, and in biopharmaceutical production to try and look for optimization routes to get the highest yields of interesting biopharmaceuticals that could be produced that way. Clinical applications is a bit more speculative because this technique is so young and because it's been available only at synchrotrons, and it's very far away probably, but perhaps looking at into the future, something like looking at cell samples in cell therapy to make sure they are what you hope they would have been in putting them back into the patient, and some sort of histopathology is another potential. But these are questions that I think there are other people here who are more qualified to answer than me. So we've been supported in this over the last 15 years of development, I suppose, or so, by Enterprise Ireland, by H2020 funding, by the Irish Research Council, and before that again by Science Foundation Ireland through awards into the group. And the idea for this particular development, which is only a part of what the group does, and is what the company is doing. The idea is to get these microscopes and to make them as ubiquitous in biological imaging centres as electron microscopes, but hopefully a little bit more useful. So that's it.